All right, so we're going to cover a new topic, and we're going to perform more magic. And here's what we're going to talk about. AX equal to B. Now, I am a professional, supposedly, applied math person, right, or mathematician. And I'm going to tell you right now that most of you probably think, you kind of know something about AX equal to B. But there's always more to learn. This is a hard problem, actually. So we don't often think about it, because we just hit backslash on Matlab. You just say, whatever, who cares? Just backslash it. It'll give me something. And it usually does. And a lot of what we're going to talk about on data sciences, right, is the fact that this matrix A is going to look like that, or it's going to look like this. It's going to be tall and skinny. In other words, you can get a lot of data this way, few that way. Or it can be like this. A few measurements, but lots of measurement in time. Okay? So this AX equal to B is going to be either massively overdetermined or massively underdetermined. That's like the generic scenario you have in data science. Okay? Now how you solve it? Of course, most of you have been solving it this way. You don't have to give it a second thought. So today we're going to give it a second thought. We're going to talk about this because in one case here, when this is a massively, right? So if you think about the vector here and multiplying this, this is a ton of constraints with very few variables. So this is massively overdetermined. In general, there are no solutions. Everybody agree with that? I can't satisfy all these constraints. There are no solutions. This one has only this many constraints, but all these unknowns. So it's massively underdetermined. So I have infinite number of solutions. Remember when the determinant of a matrix A is 0? What does that mean? It either means you got an infinity or none. And what we're going to live with now is exactly that. For these over and underdetermined systems, we're either at infinity or none. So the question is, how's this actually even working? You thought about that? You hit backslash on an over and underdetermined system, it's impossible to solve. Because there's either an infinite number or none. So if you remember, what I talked about earlier was that what we're going to do is do the following. AX equal to B, subject to. We're going to impose a constraint. This is exactly what we did for independent component analysis. Remember, I could not solve the problem. I didn't know how to pull these two signals apart. I haven't given you enough information to do so. Then we imposed constraints. We said, okay, well, how about if we say that the things are statistically independent, for instance, right? And then that allowed us to make progress forward. Everybody okay with this? It almost seems beneath you, maybe. I thought it was beneath me, and then I started learning about it, and I was humbled. So this is your moment to be humbled too, maybe, unless you know it all. Okay, but AX equal to B. I mean, this is not what you write home about, because your parents will be like, you're still on that? I thought you were moving past that. Wasn't that something you took like undergrad? You're still there? Yes, Mom. I'm still solving AX equal to B. At that point, your parents will be disappointed in you, but that's okay. We'll move past it and show you all the wonderful things you can do with AX equal to B. Okay? All right. So I'm going to start, actually, this AX equal to B process by doing, and part of why I want to go down this route is I'm going to start talking about this thing called compressive sensing. And what we're going to start looking at is just doing curve fitting for a moment. Okay? So curve fitting is of the form like this. Let me show you what we're going to look at first. I have a bunch of points, and I want to try the best fit curve through there, right? So, shoot. Hold on. I don't want to erase with my hand because then I get on my suit or on my face. And I know I can't count on you guys to tell me, like, you get a big black mark on your face. I've tried before. I've walked out of this classroom, gone to the restroom, and I have big black marks on my face. And nobody, even though you're sitting 5 feet away, said, hey, dude, you got like... So I have to be careful. I can't trust you guys. We're going to do that for a minute. So notice what I'm going to do. I have a bunch of points, and I'm trying to determine 2 parameters. Okay? So this actually turns out to be just AX equals to B when you do the curve fit, least square fitting. Okay? So we're going to do some least square fitting on this. And the thing I'm going to focus on is when we do this, there are a variety of options about how we do this curve fit, including least square fitting. And least square fitting you've done for a long time, right? You just say, well, I'm going to take these points. This is going to be my function, right? Let's call this f of x. And what I'm going to try to do is look at the difference between where my function says I should be and where the points actually are. And I'm going to minimize this. Right? So that's what least square fitting does. We typically take the 2 norm, and I'm going to show you there's some options around this that make a big difference for us about how to do fitting. Okay? And in particular, let me just show you. This is the precursor to this. What if those are my points, and what if all of a sudden I have 1 point there? Uh-oh. That was like when you brought your Chipotle lunch into the lab and you accidentally bumped the table because you were so excited, and then you got that data point. Now, could be, so remember I said it's illegal to like just remove points. You can't just remove points that are like, well, I don't like that point. I'll take it out of my data set. You can't do that. Okay? So you have data points like this. You know what's going to do this whole curve? If you do least square fitting, what does it do? It takes the difference between where you are and where the other point is, squares it. You see that distance? You made a mistake. And you're going to square that mistake. Okay? Squaring mistakes is usually a bad thing. And what it's going to give you is a line that's way off. All because you have a bad data point. And all because you chose the L2 norm. So we're going to talk about the norms that you get to pick. The reason this is important because it's generic for AX equal to B and how you want to solve AX equal to B. In particular, I keep telling you here that it's all about AX equal to B for under and over determined systems. And then when you write down a solution for me or for yourself, you've got some choices to make, right? Out of the infinite number of solutions, which one I'm going to give you, and what's the norm I'm going to use, or out of the unsolvable problem because I got too many constraints, I'm still going to minimize something for you. I want to know what is the norm you're going to do to give me a solution actually. Okay? All right. So let's pull up some Matlab. And come on. Wake up. Wake up. Wake up. Okay, seriously? You're rebooting? How did that happen? Hold on, let's see if you saw that I didn't do anything, right? I didn't like tell it to reboot. You saw I just muted this thing. Come on. Gotta be kidding me. Okay, here we go. Your computer was just started because of a problem. Ignore. All right. All right, here we go. Let's bring this up here. Then pull up. Now I gotta restart here. I think I got unmute this thing. All right. Come on. All right, just give it a second. All right, we'll do the AV unmute here. All right, okay, I got that. Actually, I wanted this. Okay, here we go. We're going to program. Oh, come on. And let's bring up this code right here. Okay, this is the stuff we were working on last time. And let me just kill it all. Okay, let's start off. Okay. So we're going to do first, I'm going to give you a set of points. And what we're going to do with these points is make a least square fit. So x is equal to, here's my x points. And I could have typed this beforehand, but since my computer died, it would not have mattered. Oops. I want 2.8, 3.0, 4.0, 4.3, 4.4, 4.9. So these are some x coordinates, and associated y coordinates are here. And we'll plot this in a second. 2.0, 2.2, 2.8, 2.7, 2.0. Okay, plot x, y, line width, 2. Okay, all right, so here's our data. Here it is. Okay, and we'll just plot it with, how about red circles? That sounds good. Okay, so here's our data, and our job now is to do a curve fit. And what I want to do with this is actually fit a line through that, okay? And so what I'm going to try to do with this is I'm going to have to solve a minimization problem. And by the way, for least square fitting, there's actually formulas for how to do this. It's not that hard. You're going to minimize the L2 error. And why least square fits are kind of nice is that you can write down a very simple formulation of this as an optimization problem. So let me just show it to you here. Suppose this is going to be my fit. A line. And what I want to minimize is the L2 square error, which means I actually have to minimize, right, the square of f of x minus the data points squared. Let's call this E. So I want to minimize this. So how do I minimize an error? Minimize, I say that word, and you think derivative is 0. Sweet. In fact, there's two parameters in here, right? So this is mx plus b minus y. So really, I want to take the derivative with respect to m, set it to 0. And I want to take the derivative with respect to b, set it equals to 0. And this is going to lead me to a 2x2 system of equations. Now, how do I know these are minimums, not maximums? Well, it turns out in this kind of thing, we do curve fitting, there's no maximum error. Okay? You could make it infinity error if you want, right? You move that fit off to infinity, and you'll make an infinite error. Kind of like life. There's no upper bound on your errors. Okay? There's only like the best you can do, and then it goes up with no upper bound. Okay? All right, so we know this. This is going to give you a 2x2, and then actually that's easy to do. In fact, this is even built in to Excel. You tell it to fit a curve in Excel. Even Excel knows, oh yeah, this gives you a very simple 2x2 to calculate. Okay? All right. But what we're going to do is we're going to actually use the fmin search command, because I want to play around with different norms, to sort of minimize that error and find these parameters through minimization. Okay? So let's do that. All right. So what we're going to do now is we're going to do fmin search. We're going to take these curves here, and I'm going to find the coefficients of this. And I'm going to do an L2 fit. In other words, I'm going to look at the least square error. So the coefficients that come out of a least square error, L2 fit. Fmin search is the command. And I'm going to do a line fit L2 with L2 error. Okay? And I'm going to initially guess that two parameters there in that line fit are 1 and 1. So the slope and the offset are 1. These are for tolerance settings, and I'm going to send in the data. But I'm also going to do one other thing. I'm also going to get coefficients for an L1 fit. Now, what's an L1 fit? The L1, instead of squaring that, the L1 just says, look at the absolute value of the difference, no square. Okay, couple simple implications right away. It's still trying to calculate a distance. Okay, that's one. Now, difficulties. Do you remember differentiating absolute values? They're kind of a pain, right? So you have to take care of what the sign is and all this stuff. So it's not as easy to work with absolute values when you do differentiation. This is trivial. This is not. Second, let's go back to this picture I drew here. If I do the L1 norm now, if I get a point like that, way out in the distance, yes, it says, look, there's a problem here, but it's not going to take that distance and square it. It's going to keep that distance, right? So it will count for those points, but it's not going to move, as you'll see here in a minute, it's not going to move this line way up here or way off of the fit. It's going to react to that point, but only by looking at the distance, not the distance squared, okay? Now, why is that important? Because often those points like that are called outliers. And a lot of what people are interested in doing is robust statistics to reject outliers. Like, how do I find them? You can't just throw them away. We've talked about that. You can't just say, I don't like that point, I'll erase it. What I'd like to do is say it's in my data set, but my fits and my regressions, I'm not going to overreact to them. Okay? So the L1 norm is a huge difference in this, as you'll see. All right. So let's go do some L1 norms. All right. Here we go. All right, so these are the generic calls, but what I need now, hey, maybe I even have them. What did I call these things? Oh, look at that. I do have them. Sweet. Okay, let's open them both up. Okay. Line L2 fit. Here's what it does. Let's go through this. Here we go. So it's a function. It's going to return an error, and it's going to minimize that error. So here's the thing I'm going to minimize, E. And what is it? I send in x naught. X naught are the two parameters, the slope, the right, so m and b that I had in there. So initially I pick them to be 1. So here's my line, mx plus b minus the actual data points squared. And I give it a guess, and fmin search iterates to try to find the actual solution. Okay? So this thing will iterate, iterate, iterate until it reaches, until the iterations, they converge to, so that each iteration does not change the solution by 10 to the minus 6. Then it quits, sends you back an answer, sends you back new values of m and b. Okay? The only difference between that code and this code is absolute value of the difference. Okay? All right. Everybody agree this is super simple? And you're kind of amazed that we're actually covering in class. But that's okay. It has a point. So let's go ahead and run them, because I get these two things, and let's plot these. So coef here is, I'll have, let's call it M, the L2 fit. Let's do this. Okay. X will be some points, let's call it XS for, it's going to go be a lin space. It's going to go from 0 to 5 in 100 points. And then I'm going to say my fit from a L2 version is going to be coef L2 1, that's the M, times XS plus coef L2 2. Okay, so that's mx plus b. With those coefficients and the y1 fit, is now just, okay. And then I can plot these. So plot, so let's plot the points. Oh, I already have them. So I already have the points up there. So we'll do a hold on. And I'm going to plot now xs, y2, xs, y1. Okay. There you go. L2 versus L1. Now, so what you see here is they're not that different. The blue is the L2 fit, and the L1 fit is whatever that color is, orangish, reddish. I want to highlight the following. So what is the difference going on? You see this point over here? That's what's actually tilting that blue down, right? It's trying to minimize these distances, and it's incurring a lot of penalty from here because I got to take that distance and square it. Right? L2 is trying to minimize these things. So it's going to say, like, okay, if I can make that a little smaller, that will minimize my score. So it takes this down. The L1 just stays on here, somehow does not act too much towards that. So in this case, you still say, well, big deal. They're pretty much they're not that different. Okay? So what's the big deal? All right, now let's make a bigger deal. Let's throw in some data. Right here. And right here, here. All right, run. Okay. Now, here's what I wanted to show you. I threw in some outliers. Here and here. Let's look at the L1 fit. Hardly changed. Right? Because it just says, I see you, but you get a penalty score. The L2 starts shifting quite a bit because the L2 is saying, I got this, I'm squaring that distance. So you can start seeing that the difference between L2 and L1 can be significant. Okay? Now here's going to be my point. How do outliers come into your data set? Let me give you some examples that I've seen in my own data analysis. So I was working on some data from Brazil, temperature recordings from the Rio de Janeiro airport, and we were looking at dengue outbreak according to temperature, looking at climate, how it associates. Okay, so we started looking at this data set, and somehow in the summer, you know, there's daily temperature. It's like a morning reading and an afternoon reading. And all of a sudden, somewhere for about a 2-week period in the summer, no data. The person taking the recordings went on vacation. There's no data there. Now, what's interesting is if you just load data and it doesn't see that, oftentimes Matlab and other programs will fill in a missing value for you, like give it a 0 or an NaN or an infinity. Do you know what your program does? Because if you don't, you have data and you have missing data, and it's being filled in, you don't know that, and all of a sudden your temperatures that sit there at high values maybe gets filled in with the 0, and your whole thing gets pulled down by it. That's one possibility. Another one, fat fingers. Have you ever had fat fingers? You're typing in a 31.5 and then a 31.6 and then a 32 point, and then you miss it. You type in a 71 on accident or a 311, because you know, if you type in data, I'm not going to say, you know, you're not flawless, you all are. But it could be that in your as you contemplate their flawlessness, you might have mistyped something. Or you copied and pasted. Have you copied and pasted and you thought you got the first character as 113, but you thought you saw all of it highlighted, but you got 3, not 113? These things happen. This is the nature of data science. You got a lot of data. It's almost always going to be flawed by something like this. Okay? That's the nature of real data. The nature, if you have that, you're going to have problems unless you figure out a way, you do some robustification. Okay? Now, it could be you're downstream from this data. You have no idea how this happened. It could be there's a very simple explanation 2 levels above you that you're never going to get back to. And so you have to do with this data, and you can't just say, oh, I don't like this data, I'll throw it away. You can't do that. Remember? I've said this over and over. You can't just do that. Here, you have it, and you see this thing hardly reacts to it. Okay? Everybody good with that? So what we're talking about here is there's a tremendous difference between L2 and L1 norms. And up to this point in your life, you've probably only dealt with L2 norms. And what I'm going to teach you is that L1 norms, L2, did I say L2? I think you've mostly dealt with L2, least square fitting, in your life. Now we're going to talk about L1 and what you can do with L1, because L1 is going to be super important for us. Okay? Good? All right. So this is the application in terms of curve fitting. Oftentimes, this is what's called robust statistics. Robust statistics are methods, just like the name sounds, to robustify your regressions and things like this. In other words, you're going to have corrupt data and missing data, and you always need some way to handle this. So John Tukey, I don't know if you know John Tukey. John Tukey was the guy who invented the fast Fourier transform. He was also the person who, 50 years ago, he was already talking about we need to move to data science. Data science is its own discipline. It's sort of this call to data science 50 years ago, more than 50 years ago. And he was also the one who invented robust statistics. And he said the following about this, roughly. I didn't hear it, but I'm getting second-hand, third-hand, fourth-hand knowledge. He always believed that it doesn't matter what kind of robust statistics you use, just make sure to use some in your data science. That's something that you should always think about. Always use something that's going to handle robustify estimates and so forth. So this is just one way to do something, okay? All right, now we're going to move on from curve fitting, which is an ax equal to b, to straight up ax equal to b, okay? And we're going to look at the implications of this in ax equal to b, because it's going to have a big impact in this idea of compressive sensing that we're going to work on. Any questions on this? Does that make sense, everybody? Yeah? All right. And what I want to just, again, having you start thinking about is different norms make a big difference. Okay. Let's throw all this away. I hope I don't need that again, because I just deleted it. I'm going to make a matrix A. And actually, let me define two parameters, m and n. And what I'm going to do is make a matrix A, which is a random set of numbers, m by n. It's going to have 100 rows, 500 columns. So, if you remember those matrices I drew, this is a short, fat matrix. I'm going to have 500 unknowns and only 100 constraints. So I have an infinite number of possible solutions. Okay? Oop, that should be a semicolon. All right. So my right-hand side B is going to be rand n, and it's going to be m by 1. Okay? All right. 100 constraints. The B is just part of the constraints, the ax equal to b. And I'm going to solve for this thing. So let's talk about solution techniques for this. Here's one. Let's do backslash. That's normally what we don't have to think. Right? This is like what you would normally do. Let's call it pre-Nathan and post-Nathan. PN and PN. So you could always say, are you PN or PN? Oh yeah, PN for sure. Okay? I should come up with something better. All right. But here, if you're PN, like as in post-Nathan, then you might, okay, here's another way to get this thing. Right? P inverse times B. That's a pseudo-inverse. Those are two techniques. I'm going to come up with others. But let's just look at even the difference here. So what I'm going to look at is, I'm going to give you a set of plots. Is these two just solved ax equal to b. Okay? And I'm going to give you another one. x3 equals lasso ab. Okay? x4 equals ridge. x5 equals robust fit. Did you know there were this many AX equal B solvers in Matlab? Dropping them on you. And it's partly to my point. This is, people think about AX equal to B all the time, right? In more sophisticated ways than we usually teach in engineering. Especially if you're in statistics, these things are fairly common. So let me do the following for j equals 1 to 5. And what do I want to do here? Oh, shoot. Okay, let me just, okay, I'll just copy and paste instead. I'll have to set up a fancy loop. Subplot 5, 1, 1. And what I'm going to do is do a histogram of x1. So what I'm going to do with the histogram is I'm going to show you the distribution of scores for the vector x that solves this problem. Okay? That's what I'm going to do with the histograms. So I'm not going to actually show you the solution vector. I'm just going to show you the distribution of values of those scores, right? After all, it's just a random matrix, right? I just made random matrix, random right-hand side, solve. So I should just get some vector. It doesn't have any meaning, really, except for the fact that if we start looking at what this histogram gives us, it's going to give us some interesting diagnostics for the solution. Okay, so let me copy and paste this. And here we go. And we're going to look at how these things vary. And it's undoubtedly going to crash, I think. Yes, okay. Let's just look at lasso again. So I was going to change this up a little bit because...
You wrote capital X.
Oh, I wrote capital X? Oh, silly of me. Where? Oh, yes, thank you. How did I do that? All right, here we go. Maybe that will work. It's probably still going to crash. Oh, shoot. What is that? 3, okay, ridge. Okay, fine. Let's comment that out for a minute. Some of these you're required to do put in parameters. Let's do help lasso. So why is it showing me that? I want to see. I think I'm going to have to give it a parameter. All right. So I know it should be fine. And help ridge. Is it telling me some stuff here? Oh yeah, I got to give it a ingredients. Look at that. Oop, that's lasso. Where's my ridge? Here we go. Hold on. Let me get ridge. Here we go. Ridge. Okay. Y, K. I got to give it a K value. K is a scalar. Let's give it like. So I'll tell you what K is in a minute. And let's try that. See if that gets me to where I want it to be. All right. Let's just do that. That's the easiest fix for now. Robust fit also has to have it. Okay. All right, I'll tell you why those are. All right. This is not going as well as I had planned. In case that wasn't clear to you. I was going to avoid doing the optimization, so let me tell you first what I was trying to do. And then I'll just do straight up optimization with CVX. So here are two different optimizations, backslash, pseudo-inverse. They're going to distribution of values. Now, both of them have a slightly different, or okay, depending on if it's over and under determined, they'll have slightly different scenarios for how they load up the coefficients. The other one I want to do now is do explicit L1 penalization. This is what lasso does. The lasso penalizes, gives you a solution by penalizing L1 norm. Okay? It says, so in other words, when you go to do this fit, here's the kind of ideas that are coming up. Solve this. And how many constraints? 100? How many unknowns? 500? I can't do it, right? Straight up, if I just write that down, there's an infinite number of solutions. So which one's it going to pick? So often what Matlab will give you is, I'll solve that and minimize the x norm. All of a sudden you have a unique solution. Okay? So normally when you hit backslash, that's actually what it's actually doing. Right there. It's saying, okay, you give me an infinite number of choices, I'll pick the one with the smallest L2 norm. We could also have done this. Minimize the 1 norm. What's the difference? So I'm going to show you. Lasso would get it to it, but right now I don't want to futz with lasso. So let's just go ahead and do CVX. CVX is a package, and what it does for you is you define a variable. Let's call it x3 size n. And what I want it to do is minimize the norm of a times x3 minus b, the 1 norm. CVX end. Okay, come on. So CVX is a package that you can just download. CVX stands for convex. It's a convex optimization package. It's a little thing on Matlab that you can just package you can download. And what I'm doing here is saying, here's my variable to solve for. I want to find x minus b. Okay, and I want the norm of that to be, I want to minimize the 1 norm. That's what the 1 there does. Okay? By the way, I could do this also with the 2 norm. So I could say I also want this solution to compare it to the others up there. And I want that to be the 2 norm. And so let's make this subplot 4 and 4. And I'm going to say, right? Now, then I want to do is just plot a hist. Subplot hist x3. Ah, shoot. 4, 1, 3. Hist x3. And let's do, and run. What? It should work, yeah. That's exactly what I had. What did it say here? Unless I have something mistyped. Okay, so yes, I did mean that. Good. That should get it. Okay. So I am typing exactly what's in my notes. So why is that not going? Minimize norm x3 minus b, yeah? Okay. Interesting day for me so far. I am striking out here. This is weird. Type double. What? Oh. Let's try this. Okay, so maybe I did it wrong here. Okay. Now it's going. Okay, sorry. Stupid mistake. Oh. Yeah, let's do this one here too. All right. So what this does is an actual optimization, convex optimization. It frames this thing up. And let me just show you what the differences are between these. Okay. Interesting. No, that can't be right. Oh, hold on. No? Okay, that's totally wrong. That can't be right. Let me cut this out for a minute here. So now it's optimizing. Okay, that's totally wrong. What is going on? All right, let's just look at the top two for a moment, because I'm copying right out of my notes. If you have my notes, it's right out of the notes. And if you look at the notes, I have exactly what I'm supposed to be getting. Not here. All right, let's just look at these two for a moment. This is, okay. So first of all, how did I solve this? How did I solve this? This is the pseudo inverse. This is backslash. Now it turns out backslash, what it does is it doesn't actually do least square regression. It does what's called, it actually projects onto what's called a QR decomposition, which has a sparse solution determined by the number of constraints. So notice here, this is the distribution of values. So these are the scores of the loadings of the x vector. And how many of them are 0? 400. In other words, I have 100 constraints, 500 unknowns. So if we did the following in class, which would be exceptionally cool, I gave you a matrix, 100 by 500, and you had to solve this thing. So, okay, before anybody leaves, solve this 100 by 500 system. You might say, like, oh, well, okay, that sucks, but there's 500 unknowns. I could just set 400 to 0. And then you might feel like, I had to get 500 unknowns. I already got 400 of them. So I just have to solve 100 by 100. And you might feel better about that for a little bit. Okay? So that's what this thing does. So this says I can set 400 to 0 and move this forward. Now what you should be seeing here in the L1 is you should see the same kind of thing. 400 of them are 0. And here's the least square regression. When you do L2 penalties, the pseudo inverse, look what it does. It spreads out everything. Okay? So why does it do that? It's trying to, the L2 norm squares things, right? So if you take a really small number and square it, it becomes smaller. So what the L2 norm wants to do is make everybody super small, because if you square it, it's even smaller. It makes none of them 0. Just tries to say everybody eats a little bit of this up, and as small as possible, because I'm going to square you all at the end of it, and I want anybody to be big. Anybody who's big is going to create a problem for me in my score, right? Because I'm going to square that. So I want to make everything small. Now the L1 here, which is puzzling me, I just feel like there's got to be a simple mistake here, but gosh, do you see, anybody see it? Because I don't. That's exactly how I might code in the notes. In the notes, by the way, just to prove it to you, if you download it, it looks, yeah, the L1 looks a lot more like the top picture. I'm on fire. I'm going to go home after this class and just go back to bed and just sit there and just call it a day. That sounds pretty good, right? All right. Okay, that's, you're going to have to just trust me on that one, even though this is kind of crazy. I don't know why that's not working out. Yeah, it's right there. All right, fine. All right, so now what we're going to do is do the opposite case. We're going to now do this. 500 by 100. So now what we have are 500 constraints, 500 constraints, only 100 unknowns, right? There's no way we could satisfy 500 constraints with 100 unknowns, unless many of those constraints are the same, right? But that's just generically not the case, because I made a random matrix. There's no way to get a solution to this. So what we do, there is no solution. There's nothing that satisfies AX equal to B. So what I'm going to do instead is say, okay, I can't satisfy this. I will instead say, I want to mostly satisfy it. I'd love that to happen. It can never happen. So I'll just say minimize, for instance, that. I can't satisfy x equal to b, but I'm going to try to make ax minus b to be as small as possible. Okay? That's what happens in an overdetermined system. Now again, how I'm going to do that? Do I want to minimize that with the L2 norm, the L1 norm? So let's show you some differences here. And So here we go. Here's my matrices. And so what I'm going to do with this is start to solve these. To do this. And again, I can do the backslash. I can do the pseudo inverse. And now when I do this, I know why. Okay, hold on. You remember when all my papers fell? Remember to start off my awesome morning? Well, 2 pages here got shuffled that I'm just starting to realize. Let's go backwards in time. And we don't have time to go backwards in time. Actually, what I was solving here was what you would do for the undetermined case. What I'd really want to do in the undetermined case, I actually can solve AX equal to B. Right? Because I only have 100 constraints and 500 unknowns. So there's infinite ways to satisfy it. So let's go back to this case here where it was like this. I could do the same for this. Actually, okay, let's just run this example to show you what would happen. And if you look at my notes, it actually works out for the other case too. Just, you should be reading my notes anyway. Yeah, okay. It's going to take some time to fix. So let's pretend today maybe didn't happen. But if you look at the notes, all the code is there. You can download the CVX package. What's my main point? My main point is this. There's 2 norms we're going to work with. L1 and L2. And unfortunately, it didn't show up here. What L1 does is it promotes what's called sparsity. The L1 norm, what you would have seen there, is it tries to set as many things to 0 as possible. The L1 gets penalized for every non-zero entry. So it says, how many can I set to 0, and then just make as few as possible non-zero. Whereas when you do L2 regression, right, it's trying to make everything small because it gets to square it. So things that are small and you square it makes it even smaller. So what L2 and L1 look like are fundamentally different. But what the L1 is going to allow us to do in this next lecture is going to show us this idea of what's called compressive sensing. Take a small number of measurements and recover an entire signal. Okay? It seems like an impossible trick, but I'm going to show you it all depends upon that L1 norm. All right, awesome day. Hey, enjoy your day.